Well, good day, everyone. This is Chris back again with the Ancient Scholar. I should let you guys know that a lot of these crystal field theory videos I'm actually recording over Christmas and New Year, but my internet access at home is I'm only getting about 1.5, 1.7 megabyte per second speeds, and my upload speeds and bandwidth are much lower. Um, so that probably means that I won't actually be posting these until after New Year when I'm actually back at the college and I can use their high-speed internet to get these videos uploaded because I often have problems uploading at home. But I am doing all these videos over the break. And my video traffic will probably slow down substantially after well, probably after the 6th, just because our classes at the college will start. I'll be teaching a lot, and then I'm actually taking classes working toward a master's degree. And this semester will be very busy for me there as well. But anyway, let's get back to business. So I think we're in a good place to talk about crystal field theory proper. Okay, so this is what happens. This is how we look at it. Crystal field theory, we model a metal like it's positively charged, and often it is, and then we model the ligands like they are negatively charged, even though they may or may not be. Okay, and then basically the intuition is, oh, the negative charge is attracted to the positive charge. So the kind of the basis of crystal field theory is we kind of pretend, in a sense, we model the coordination complex as though it is an ionic bond. Okay, that's fundamentally what's occurring. Even though we know it is not an ionic bond, the model of pretending it's an ionic bond really makes some good predictions. So that's kind of why we do it. Okay, so let's now talk about the d orbitals, since they are really interesting in crystal field theory. So in a neutral, okay, a neutral or naked, maybe a naked, we'll say a naked metal, a naked transition metal, the d orbitals are degenerate. Okay, the d orbitals are degenerate. So if this is energy here, the d orbitals. Okay, so I've got 1, 2, 3, 4, 5. And I'll actually just review the names of them because occasionally that is important. So I have what's called the dxy orbital, the dyz orbital, that is z, not a square. Let's see here, dyz, and then a dzy orbital, and then a dz squared orbital, and then a dx squared minus dy squared. Okay? And all of these 5 orbitals have degenerate energy levels in a naked metal atom. However, as the ligands come in, because these d orbitals, these d orbitals have electrons in them, okay? As those ligands come in, the electrons, so if these are electrons on my ligand, those electrons are going to interact with these d orbitals, and if these d orbitals have electrons in them, if a ligand is coming near a d orbital, there's going to be some repulsion here, and what's going to happen is the energy levels of these d orbitals are going to split. There's going to what we call energy level splitting. Okay, so we'll just rewrite this. So here is a naked atom here. Okay, and my d orbitals, okay, are all at the same energy. But then what's going to happen is the ligands are going to come in and they are going to split the energy levels. And there are 2 ways that the energy levels can split. There are two ways this can happen, okay? The first way is what we call a weak field. All right, a weak field. So if you can imagine, this is energy here in the, okay. So what's going to happen is 3 of the d orbitals, 1, 2, 3, are going to be at a lower energy, and then 2 of the orbitals are going to be at a higher energy. And the difference in energy here, so the difference, so this is energy here, and I'm not going to actually put values up or anything like that, but the difference in energy here, so the difference between the low and high is what we call delta, okay? That is often what you will see used. Delta is just the energy, all right, the energy difference, okay, between the high and the low, okay, that's what we call the delta. And in a weak field, the delta is small, okay, there is a small difference in energy between the splitting. There's a very small splitting, okay. And oftentimes you may hear people call the 3 orbitals down here at the lower energy, people will often call these the T2G orbitals. All right, the T2G orbitals, and then the orbitals at higher energies, okay, orbitals at the higher energies are what we call the EG orbitals. All right. So what has happened is the 2 orbitals here, these 2 orbitals up here are interacting more with the ligands. Okay, the electrons and the ligands are closer to these orbitals, and these orbitals down here are less affected by the ligands. And this has to do with how the d orbitals are oriented in space. Some are oriented along the XY axis and the Z axis and all that. So the orientation of the d orbitals and how the ligands come in affects which orbital it gets split up and down. I'm not going to go into that detail quite yet. Just I want to make sure that we're good on what's actually the bigger picture. Okay, so this is a weak field. All right. So what I'm going to do is I'm just going to clear this now, and I'm going to put my weak field back up here. Okay, so 1, 2, 3, 4, 5. That's my weak field here. Okay, weak. And then, okay, I also can get something called a strong field. Okay, so 1, 2, 3. I still have my splitting, but here's a difference. Okay, 1, 2, 3, 4, 5. So what have you noticed here? So when we look at the energy splitting, okay, on my weak field, delta or del is very small, but if we compare that to the strong field, the delta is very high. Okay, there's a very large gap in energy. All right, so this is a strong field, this is a weak field, and some ligands are better at producing weak fields, and some ligands are better at producing strong fields. And then the difference in this energy here is what we call the splitting energy, and that is the energy of the crystal field, hence the term crystal field theory. All right? Okay, so now, why do we care? Why do we even care? Well, this is why, and I'll pick a green. Okay, so what's going to happen is, why we care is because when it comes time to start putting electrons in these d orbitals with their energies split, the electronic configuration is going to be very different from weak to strong. Okay, so let's just say that for the sake of this scenario, I have 4 electrons that are going to populate, okay, the d orbitals. And what I want to do is I want to compare the weak field to the strong field. Okay, so 4 electrons. Okay, so let's start at the weak field. So we'll use Hund's rule, the Aufbau principle. So I'm going to put electron here, right? I'm going to fill my lower energy at first. So 1, 2, 3. Here's the thing. Now that I get to my 4th electron, where do I put it? Okay. I could put that 4th electron up here, right? Because these are open orbitals. But the problem is it's a higher energy level, and electrons would rather be at the lower energy levels, right? But here's the problem. If I put the electron down here, I'm going to have to pair it with another electron, and we know that electrons don't like being around each other. They repel one another. So in the situation of a weak field, the energy difference is so small, the splitting is so small, the delta is so small, that the electron would rather go up to the higher energy level than have to pair up, okay? So the electron would rather pop up into this higher energy level and then pair up down here, okay? Let's contrast that with a strong field, okay? So in a strong field, I'm going to put my 4 electrons in. So 1, 2, 3. Now, what's going to happen to the 4th electron? The 4th electron could go up here, but this is much higher energy, or it could go back down here and have to pair up. Well, a strong field, the energy difference, the crystal field, is so large that the electron would rather pair up down here than go to the higher energy level. That is not the case with a weak field. So what happens is I get a different electron configuration between strong and weak fields. This can affect our the properties of the complex, of the coordination complex. And the 3 properties that we really look at is let's do 2 properties for now. Let's talk about something called the Spectrochemical Series, okay, and magnetism. Okay, these are 2 properties that are very, very accurately predicted using crystal field theory. Okay, so what we have here is, if we look at the weak field versus a strong field, what do you notice is going on? Well, what I have in the weak field is I have unpaired electrons. Okay, you can see that the electrons have a tendency to be unpaired. They're unpaired. Whereas in the strong field, there's a better tendency for electrons to pair up. Well, if you remember, when we talk about paramagnetic versus diamagnetic, okay, so something is paramagnetic, that means it will respond, it is attracted to a magnetic field. Okay, it will respond to a magnetic field, paramagnetic. Okay, it will easily respond to a magnetic field. All right, whereas diamagnetic, not so much. What makes something paramagnetic is the presence of unpaired electrons make something paramagnetic. Okay, which one of these has more unpaired electrons? They both have unpaired electrons, but the weak field has more unpaired electrons. I have 2 unpaired electrons here in this case. In this case, I have 4 unpaired electrons, and even though we're dealing with the same number of electrons, the weak field has significantly more unpaired electrons. So the weak field, the weak field tends to be paramagnetic, okay, or more paramagnetic than the strong field. The strong fields tend to be more diamagnetic compared to the weak fields. The weak field also has lots of spin, right? If I have a spin up and a spin down, that they cancel out and there's no net magnetic moment. There's no net spin going on there, right? So that cancels out. So if I look at the spin, the sum of the spin is plus 1/2 1. So over here I have 1 unit of spin, if you want to look at it that way. Whereas here I have plus 1/2 1, 1.5 2. I have 2 units. I have twice the spin. And we often call weak fields, okay, a high spin, okay, a high spin system, or a high spin complex, whereas the strong field, okay, tend to be what we call low spin complexes, okay. These are all definitely all words that you're gonna want to know very well. High spin just means weak field. Electrons will tend to go to the higher energies, so they don't have to pair up. So you have more unpaired electrons, so you have more spin, okay? Whereas your strong fields have less spin because the electrons tend to pair up versus going to the higher energy levels. All right? Okay, so we've got that out of the way. All right, now let's compare the spectrochemical series. And what that means is that the metal complexes often tend to be very colorful. Okay, they are very colorful. And they're very colorful due to the electrons being able to transition between the different orbitals. So if I have energy, maybe in the form of a photon, a light comes in, that energy can come in, and that energy can hit one of those electrons, and that electron will absorb, and it'll pop up to a higher energy level, so it'll absorb, and then what can happen is the electron can then fall back down, and it can release energy. Okay, so when we look at this, the amount of energy that can be absorbed is going to differ between the weak and the strong field, or the high spin and the low spin fields. And so as a general rule of thumb, okay, so let's start over here at the weak field. As a general rule of thumb, because my weak fields tend to have lower, okay, the energies, the delta is small, they tend to absorb, okay, they tend to absorb lower energy light. Okay, so they absorb red light. Absorb red light. Okay, so here's a question. If you're absorbing red light, then what are you reflecting a lot of? Well, if you're absorbing the red, that means that you are not absorbing the higher energy light, and blue light tends to be higher energy, so they absorb red light, but they often appear, okay, more blue-ish, we'll say, more bluish, okay? So the weak fields absorb red light, but tend to appear, when you look at them, they tend to appear to have colors that are the more bluish, if you will. However, if we look at the strong fields for an electron to transition to a higher energy level is going to have to absorb more energy because this delta here is larger. So these tend to absorb, okay, absorb more bluish light. All right, more bluish light. And so they tend to appear, okay, they appear more reddish, because they're absorbing blue light, but they are reflecting the red light, whereas the weak fields are absorbing red light and reflecting more of the blue light. And this is what's known as the spectrochemical series, okay, or this is actually the starting point for the spectrochemical series. Okay, so before I finish up, let's just talk about what makes what ligands tend to make strong versus weak fields. So imagine that, and it's a kind of a continuum. Okay, so strong, I have strong over on this side, and weak over on this side, and the different ligands that tend to be strong. So your strongest ligands tend to be the cyanide ion and carbon monoxide. Okay, and then we will go weaker than that. That tends to be NO2 negative. And then ammonia, NH3, and then water, H2O. Okay, and then hydroxide ions, and then fluorine, and then chlorine, and I'm running out of space, aren't I? So let's do that again. So strong, weak, maybe I'll change this up a little bit. Here we go. Okay, so let's try that. So strong, so cyanide, all right, carbon monoxide, and then I have NO2, all right, and then NH3, and then H2O, and then hydroxide ion, okay, and then fluorine ion, and then the chlorine ion, and then the bromine ion, and then the iodine or iodine ion. So you can see that the halogens, fluorine, chlorine, bromine, iodine, halogens are important. Okay, so basically what this is a continuum. These over here produce stronger fields than these over here. So you know, the cyanide ion is going to produce a stronger field than the ammonia, whereas water would produce a stronger field than, say, bromine. Okay, so this is kind of a continuum, and it's helpful when comparing them. So this is just kind of some common ligands that you run into in basic inorganic chemistry. So it's not it's helpful to kind of memorize them. And I should say that there's not really like a fine, hard line that delineates absolutely what's weak or strong. But, you know, as a general rule, you might be able to kind of draw it right in here and say that these are generally going to produce weak fields. All right, and then these over here will produce strong fields. But kind of like, you know, right in this area is kind of a gray area, a transition area, and that may or may not produce a strong or weak field, and a lot of that just kind of depends on the exact metal that's involved as well. But this is kind of a general rule of thumb. Okay, guys, I'm going to cut this off. Hopefully you found this video helpful, and as always, thanks for hanging in there.